Hi, how are you?
How are you?
Good. Wow, it's really raining out there, huh?
Yeah.
We could sure use the rain, so hopefully it'll last for a little bit in terms of snow cover or snowpack or whatever. Hello, how are you today? Said, how are you today?
Oh, good. How about yourself?
Pretty good, pretty good. Well, think we'll go ahead and get started here and I think we got some interesting stuff to go over. I think it'll be fun. But let me go ahead and open us up in prayer and I'll give you a sense of what we'll do. So, dear Heavenly Father, Lord, thank you very much for the chance to work with the students in this course. Lord, I pray that the material that we're covering will be clear. Pray it can be an enjoyable process of learning about data structures and it's going to be helpful for them to get the job of their choosing in the future. Pray you'd also help them in their spiritual formation, Lord, that all the chances that they can study scripture from people that are experts in their fields, help them to absorb that material and the theological concepts that they're getting exposed to, help them to take this all into their heart and cherish it and be able to use it in their time of need in their future. Plus, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. So actually, what we're going to be talking about today, we introduced it last time. We got a chance to get an introduction into sorting. And so hopefully what you're seeing is each week, each lecture, we get a chance to be building on the concepts we've already been talking about. And I tried to select a handful of abstract data types that we're then coding to from two perspectives, from a back-end perspective of actually implementing those ADTs, and then from a front end, an application of creating something with your project to make it real. So last time we covered three different types of sorting approaches, something called the selection sort, the insertion sort, and the shell sort. So that's what we got a chance to be exposed to last time. And now for this chapter, we're going to be talking about three other methods: the merge sort, the quick sort, and the radix sort. And so I'm going to talk about these since we didn't talk about them last week. And then I'm going to flip over to the video notes and we'll have three that will cover that way. But I just wanted to give you an introduction to the merge sort, the quick sort. There isn't a video note for the radix sort, so I'll get a chance to just walk you through a few basic charts that will give you a sense, and then we'll do a comparison of all six of these. And you can see that instead of going from n squared, we get it down all the way to n, big O notation, n. And so that definitely is something that's worth doing. So the first one is a merge sort. This is chapter 16. So and so we'll get a chance to be talking about merging arrays. And then the real key thing that really makes this work quite well is when we do it in a recursive approach. And so that's what we'll get a chance to start. So we'll do this divide and conquer approach. We're going to be seeing this a couple times. And so it divides an array into halves. And then when we start to think like the quick sort, it's not necessarily that it has to be exactly halves, but the merge, we're going to try and make it half. And so we sort the two halves. So you sort the lower half, and then separately you sort the upper half, and then you merge them together. So the algorithm for merge sort is usually stated recursively, and major programming efforts is in the merge process. So we have a couple of things here. So I think the next couple of charts might be a little bit easier to follow than this. And so here we have an array that we want to sort. So we divide it into two. So you merge this, you sort this lower half and you sort this upper half, and then you figure out, well, which one at a time, which one's lower. So is it the first one or the second one? You can see here, this upper half, the first two were the smallest, and then we do the third, so which is the first one in this lower half, and then we gradually get to this overall merging. So this is for a recursive, we want to bring this down yet a little bit further. And so this is the pseudocode for that. I'm not going to go through that here, but rather I'm just going to be focusing on this picture to show you what it's like. So we have this one, we have an array of 8 items. So what we do recursively, we take the bottom 4, and then recursively break that into the bottom 2, and then the upper 2, and then we get to our base case, and we figure out what that is. And so basically, we then start to roll it back up. We merge those 2, we merge these 2, and then we merge those 4. We do the similar fashion on the upper half, and then voila, we get to the final stage where we have the merged results. And so I think this is I think this is big O notation 1.5 to the 1.5 power or so, but we'll get to that at the end of this quick review that I'm going through here. So here we have the algorithm for the merge sort, and so we do it from a recursive approach, so we're calling merge sort within the merge sort, and so that's what we have as we go here. We'll get a little bit more detail about this in a few minutes here. So just to review, so we merge it, we split it in half, and we do this divide and conquer, and we try and make it exactly the same size for the upper and the lower. If it's like you see have an odd number, then one of them will have one more than the other, but it's basically pretty much the same thing. So we have the recursive implementation of that. And so, yeah, and so the efficiency of this is big O notation n log n, as compared when we had the worst case scenario when we talked about the last chapter was n squared. So maybe easier to comprehend, but it doesn't perform quite as well. You can do it with an iterative approach. It's less simple. It needs to control the merges, and it will be more efficient. Will be more efficient of both time and space, but trickier to code without error. So maybe not the best thing to think about that. So I recommend just going with the recursive approach, but just one more slide. So for the iterative, you start at the beginning of the array, you merge pairs of individual entries to form 2-entry subarrays. Return to the beginning of the array and merge pairs of the 2-entry subarrays to form 4-entry subarrays, and so on. And after merging all pairs of subarrays of a particular length, might have entries left over, and then you have to deal with those. Java has built-in things for sorting, and so for the merge sort, it's called sort, and you either can those are some of the specifics that are laid out there for the built-in. I'm not going to focus on that right now. So that's the first one, is a merge sort. So it's a divide and conquer approach. It reduces the big O notation to n log n for this. And now with a quick sort, it divides an array into 2 pieces. Now they don't necessarily have to be the same size. Pieces are not necessarily exactly the halves. And you choose one entry in the array and call it a pivot. And then so then we partition the array, and we'll show a graphic, I think, that'll help you to get a better sense of that. When the pivot is chosen, the array is rearranged such that the pivot is a position that it will occupy in the final sorted array. Entries in positions before pivot are less. Entries in the position above are greater than or equal to that pivot point. We have some pseudocode here of showing how that would work. And this just gives you an idea of the pivot. So everything less than the pivot is smaller. Everything larger than the pivot is larger than that pivot point. And so that's what we've got here. So a quick sort partition. So we start so we have the pivot point. So say this is the bottom half. And so the goal is to have everything less than that pivot at here. So we move all the smaller items towards the beginning. Oh. So I think this is one that's in the video notes, and so I'm not going to focus on this too much. I'll defer to that to have a better explanation of this. But this is starting to show some of the parameters we'll be using, index from right, index from left, when we actually get into some of the implementation. So this is just walking through the partitioning strategy. So we have the median of the 3 pivot selections. Okay, so I'm gonna, like I said, I'm gonna defer to the video notes to give some more thoughts on this, but we then have the pseudocode. We saw the sort of general approach, the pseudo, and then we have the pseudocode, and then we have the actual code, and voila, looks it's fairly short in size, and we have a recursive approach to see that. So I may just come back to these lecture notes at the very end after I go through we'll do some 3 video notes to cover this. And so quicksort will be one of those things that we'll talk about. Since this isn't in the lecture notes, I'm going to spend a little bit more time talking about this radix sort. And so this one, it does not use comparison. It treats the array entries as if they were strings that have the same length, and you group integers according to their rightmost character digit into buckets, and repeat this with the next character digit all the way until you're done. And so let's use an example here that we have things with 3 digits. And so here you distribute the original array into 3 digits. You break it up into these triplets here, and then you're going to sort those one at a time. So first of all, we look at the rightmost, and so that would be 4, 0, 9, 3, and then you put them in buckets. And so all the ones that end in 0, all the ones that end in 1, 2, and so forth. And so we have ones that end in 0, one that ends in 3, some that end in 4, some that end in 8, and some that end in 9. So that's how we put those together. So thus, we have them all binned. So all the ones with our 0 are like that, and we put them in the order which one is smaller first. And so we have 210, 220, and then we move on to the up along the way we have that. So these are all the ones that end in 0, ones with 3, then 4, 8, 9. Then we do the next digit, which is the second one. So we bin those. So we take these, any one of those that has the center digit that is 0, we put it here. The ones that have a center digit with 1, we put them there. Ones that have a second digit 2, we put them there. And finally, the one that have 9 as a second digit, we put them there. We put them back into the array, into that semi-ordered conglomeration. We have that. Then finally, we do it for the most significant digit. We do the same strategy, and then we get this. So we get this finally, the array is now sorted. So we're using these 3 digits to be the basis for what we're doing. So maybe if you had have any of you guys ever heard of ASCII code? Some of you have. And so it's basically, it's a binary representation of letters. And so A has one binary ASCII code, B has another. And you could be thinking about these 3 digits representing an entity of some sort. And so when we're done, we've sorted those entities using the strategy of what's laid out in the radix sort. So this is a chart that I wanted to make sure that I covered before we move on to the video notes, is just to give you an idea. So the easiest to understand was this selection sort, and we covered this last time. And so, but across the board, it has a big O notation of n squared. The insertion sort, at least for the best case, is now a big O notation n, but everything else is still more complicated. The shell sort that we talked about last time, for the average and worst case, it reduces down to n to 1.5. And that what we did is we took, like, you had like a middle thing that you declare, and then you have like, you pick one and says which one is greater, and then you swap them. And so you just swap things at a time. And so that actually performs better. This quick sort that we'll be watching a video in a few minutes actually does a little bit better. It does n log n, except for the worst case. And then the merge sort across the board, it's n log n. And this merge sort is this divide and conquer approach that I talked about. And finally, this radix sort is you're trying to take advantage of the the characteristics of things that you're sorting. And if you can be taking advantage of this type of a structure, then that can be a really good sorting algorithm, and it gives you a big O notation of n. So that's just a quick run through for these more complicated sorting strategies that I wanted to give a little bit of an insight into before we go to the video notes. So the merge sort, I think that's probably the easiest to get your head around, divide and conquer. Then the quick sort, it actually, you create a partition and you start to do a slightly deviant version from the merge sort. And then the radix sort is basically you're using some artifacts of the digits within your collection that's helping you to do a quick sort across the board. Okay, well, let's go to the video notes. Let me share my screen again. So we're going to go over the selection sort, the merge sort, and the quick sort. So the selection sort was, I think that was the first one that we covered. And so this would be fairly easy to understand, but not going to perform quite as well. So let's just get this configured here. I have to check my sound. This is the wrong one.
This lecture presents the selection sort algorithm. Imagine that you want to rearrange the books on your bookshelf by height, with the shortest book on the left. You might begin by tossing all of the books onto the floor. You then could return them to the shelf one by one in their proper order. If you first return the shortest book to the shelf, and then the next shortest, and so on, you would perform a kind of selection sort. But using the floor or another shelf to store your books temporarily uses extra space needlessly. Instead, let's leave the unordered books on the bookshelf and select the shortest book. We find the smallest book by starting at the leftmost book. We assume that it is the smallest and mark it with a star to remember where it is. And then search through the other books, comparing them to the book with the star. If a book is smaller than our current smallest, we move the star to that book and compare future books to the newly starred book as we search for the smallest. When we get to the end of the bookshelf, the smallest book has a star. We then swap the smallest book with the book in the first position. Our first book is in its correctly sorted position. So now this first one is sorted, and then we'll get another one. Then the first two are sorted. And then, so it's going to be easier as we go through this set of elements that we're trying to sort to know where we're going to be putting it.
Initially, we have to go one at a time because you don't know which one, where it's gonna go. So this is what's starting to be laid out.
We now look for the second smallest book. Since the first book is in the correct position, we begin at the second book and repeat the process. Once found, we can swap the second smallest into the correct position. Then we repeat the process again, beginning with the book in the third position. What we've been doing is dividing or partitioning our bookshelf into a sorted portion and an unsorted portion. Books in the sorted portion do not need to be examined because they've already been placed in the correct location. So each time we need to find the next smallest, we only need to search the unsorted books, which we do here, and we perform a swap. The fifth book is already in the correct place, so we do not need to swap it. And the last remaining book should be the largest and is already in the correct place. This sorting algorithm, where we find the smallest, swap it into the correct position, and then continue searching for each successive smallest, is called the selection sort. The main activity we perform is a sequential search through the unsorted portion of the array, looking for the smallest item. Let's create a method, getIndexOf, that searches a portion of the generic array of compatible objects and returns the index of the smallest item in the search portion of the array. As we think about implementing,
So there's some syntax here that may look a little bit odd, but this is, especially in the beginning, just, copy and paste this. Like to do a sort, you have to have things comparable. So that's, we see that we have this comparable, and here is a syntax here. So you need to be including this as an element for this method, or having it included for a class. We'll see that. And so now we're just trying to define this particular method.
the selection sort, we first consider some activities we perform repeatedly. To help with the implementation, let's think of storing our books in an array. The main activity we perform is a sequential search through the unsorted portion of the array, looking for the smallest item. Let's create a method, getIndexOfSmallest, that searches a portion of a generic array of comparable objects and returns the index of the smallest item in the searched portion of the array. By defining the generic type T, as you see here, we are able to compare objects of type T to other items that are in the same class as T, and also objects in the superclass of T. The parameters in our method are the array of objects to search, and since we're only searching the unsorted portion of the array, we need to pass the index of the first entry to search and the last index to search. We begin by assuming the first entry is the smallest, and then loop from that entry through to the last. We compare each entry to the entry we think is the smallest. If the current entry is smaller, we save that value and its index and use that as the smallest item in future comparisons. When the method ends, we can return the index of the smallest entry in this portion of the array. After each time we find the smallest entry in this unsorted portion, we have to swap it into the correct position. So we need a short method that can swap any two items in an array of objects.
So we have two private methods. So these are things that are just used in our implementation. They're not exposed to a user or somebody writing an application.
Let's now look at how we would use those methods to help us implement the selection sort. The basic idea is to find the smallest entry and swap it into position. Then find the second smallest and swap it into position, and then continue until our starting position has moved to the end of the array and there's only one entry remaining. We send our selection sort an array of objects of the generic type T. Then we use a for loop to repeatedly search for the smallest item and swap it into position. Each iteration of the for loop increases the index of the starting entry in the portion of the array to search. The loop control variable index serves as a line between the sorted and unsorted portion of the array. When the for loop terminates, the array is sorted.
So once again, this looks deceptively short. That's because there was two methods we had just previously that we spoke about. The getIndexOfSmallest and swap. So this just gives you another coding strategy that you might want to implement.
The first time through the loop, we search the entire array and then swap the correct entry into place. Then the variable index is incremented, and we find the index of the next smallest entry in the array and use that index to swap the entry into the second or correct location, and then continue until the array is sorted. Let's examine the entire selection sort implementation so we can determine big O for our algorithm. We begin by finding the smallest entry in an unsorted portion of the array, beginning with the very first item. To find the smallest entry, we iterate through the entire unsorted portion of the array, comparing each entry to the current smallest entry. If the array has n items, we need to perform n comparisons. Therefore, get index of smallest is order at most n. After finding the smallest, we swap it into the correct position. Every time we execute a swap, the same 3 steps are executed. The number of operations is independent of the number of entries in the array. So swap is order of at most 1. Therefore, each iteration of the for loop is order of at most n for the method get index of smallest plus order of at most 1 for swap. This simplifies to order of at most n. Our for loop must execute n-1 times, so it calls get index of largest and swap n-1 times. This results in an order of at most n squared for the selection sort.
So it's not efficient. It's probably straightforward to understand. And so this gives you a basis for us to maybe just to do something that you could easily code up, you could use this approach. Okay, so that's the first one. And so going back to this comparison chart. So that is the selection sort. So here we have that. It's n squared across the board. So we have that. And now we're going to next do the merge sort. Merge sort is across the board n log n. And then we'll have the quick sort. The quick sort is not quite as good as the merge sort, but we'll be looking at these two comparisons with a couple of video notes. So let's go ahead and do the merge sort first.
Our previous sorting algorithms, the selection sort and insertion sort, were fine for small arrays, and they can even be a reasonable choice if you need to sort a larger array once. Additionally, the insertion sort is a good way to sort a chain of linked nodes. However, when you need to sort very large arrays frequently, those methods take way too much time. Because they are order of at most n squared, the time to sort the data set can grow very rapidly as the size of the data set increases.
So once again, what they said is like you don't automatically just throw something away in terms of an approach. You want to consider what is it that you need to be doing. There are times when a selection sort might be okay, but if you're going to be doing a lot of large numbers, then other than say like doing a chain, like they said, this is where you want the direction you want to go.
Recursion can help us to sort much more efficiently. We're going to use a divide and conquer strategy on our data set or array and greatly improve the time efficiency of our sort, giving us order of at most n log n.
So that may seem a little bit abstract to be thinking about it, but here we get an example. N squared, you can see how this grows. So 1,000, it goes from a million down to 1,000. That's a huge difference. And so that in itself is worth it.
The merge sort divides the array in half, then sorts each half recursively. Then it merges the sorted halves back together. This doesn't sound very complicated, and it's not. The most complicated part is merging the two sorted arrays after the recursion. To merge the two sorted arrays into a new array, we can take advantage of the fact that the smaller arrays are sorted. We'll compare the first entry in each array, Copy the smaller of these two items to a new array and then repeat the process until all of the entries from one array have been copied to our new array. We then copy the remaining entries from the other array into the new array.
So a lot of little tidbits here. You compare the first of each item because they're sorted. You copy the smallest and you continue until one of them is empty and the other ones are sorted, so you just stick them at the end. So thus we have our pretty close to the pseudocode that we would use for doing this merge sort.
To see how this works, we'll begin with array 1, a sorted array containing 4 entries, and array 2, another sorted array with 4 entries. We'll merge the entries in these two sorted arrays into another array sorted, but we want to place the entries from the first two arrays in such a way that the array sorted is sorted when we're finished. Notice the array sorted has enough elements to hold all of the entries from the first two arrays combined. To begin the merge, we compare the first entry in array 1, 4, to the first entry in array 2, 9, and copy the smaller entry into array sorted. Since we copied the first entry from array 1, we now compare the next entry in array 1, 13, to the first entry in array 2, which is still 9. And copy the smaller entry into the next position in array sorted. We next compare 13 to 11. 11 is smaller, so we copy that entry into array sorted. We next compare 13 to 33. 13 is smaller, so we copy that entry.
So it's always the last element that's still remaining. You're comparing it with the last entry that's still remaining in the other half. And all these are sorted, so it's just pretty easy to have this all work out.
Then 25 is compared to 33, and we copy 25 to array sorted. We continue in this fashion until all the entries in one of the arrays have been processed. In this example, it's array 1 that is completely processed first. We then copy any remaining items from the other array, or array 2 in this example, into array sorted. At this point, array sorted contains, in sorted order, all of the entries from the two smaller arrays. For our merge sort implementation, the two smaller arrays to be merged are not two separate arrays, but two adjacent sequences of elements in the same array. This does not impact the logic of our algorithm, only the bookkeeping we must perform when tracking indices. After merging the two segments of elements into a new array, we must copy the entries back into the original array. This is an important implementation detail that keeps us working with the same array. For example, here we have an array of 8 elements that has 2 sorted halves. Entries 0 through 3 are sorted, and entries 4 through 7 are sorted. Our temporary array has 8 elements also. We can copy each entry from the original array into this array using the algorithm discussed earlier for merging two arrays. We simply treat each segment of elements as if it was a separate array. After we've merged the two halves, we must copy each of the entries back into the original array so that we can continue with our merge sort algorithm. Let's look at the method that will merge our two sorted array elements. What does our method need in order to merge the two sorted segments of array elements into a combined sequence of sorted entries? We need the array to sort, that is the parameter A. We need a temporary array, temp array, where we can copy the entries as we perform the merge. First is the first element of the left or first sequence of elements, and mid is the last element of the left sequence or half. These two parameters delineate the left half of elements to sort. The right sequence of elements begins at mid plus 1. Since we can compute that, we do not need it as a parameter, but we need to know where the right sequence of elements ends, that is the parameter last.
So this we can see all the things that we need. We don't manipulate the original array. We have a temp array, and then we start to put those in order. We have two subarrays, and so they go to first to mid, then the second half is mid plus 1 to last. So that captures everything that we need to do this merging.
We need these three parameters since the two halves may differ in the number of elements in each. As was presented in an earlier lecture, when recursively processing an array, if the array has an odd number of entries, One division will have one more element than the other. In our examples here, we have the array that contains the two sequences of elements that must be merged, our temp array that we will use to copy the merged entries, and in looking at the indices on our two array segments, we can see that first is 8, last is 15, and mid was passed as 11. The entire array A and the entire array temp array were passed to our method, but we use the indices first, mid, and last to focus our algorithm on the specific part of the array we need to process during this call. Our algorithm is going to require a lot of bookkeeping. The first bookkeeping variable is begin half 1. That represents the next element from the left sequence that we're going to compare. It is initialized to first so that we begin at the leftmost element. End half 1 represents the last element in the left sequence. We use this to determine when we've completely processed the left half. It's initialized to mid. Begin half 2 represents the next element from the right sequence that we're going to compare. It is initialized to mid plus 1 so that we begin at the leftmost element of the right half. End half 2 represents the last element in the right sequence. It's initialized to last. Index is used to track the location and temp array where the next stored entry is to be placed. Now we've initialized all the tools we need in our implementation of the merge algorithm. And we're ready.
So I like the fact that they're using comments, and so they walk through it, but they also give this nice summary comments to give you further explanation, even beyond what they have with their naming convention.
To merge the two sequences. Our merge algorithm compares the first item in each array segment of array A, copies the smaller item to temp array, and then repeats this process until one of the array sequences in A is completely processed. We use a while loop to repeat the compare and copy steps. As long as the beginning of each half is less or equal to the beginning of the respective half, we continue to process elements. The processing is done with an if statement. We compare the two entries at begin half 1 and begin half 2. We copy the smaller into temp array at the location indicated by index and increment begin half 1 or begin half 2, depending on which array sequence had the entry copied. After the if statement completes, we increment index so that the next entry placed in temp array is placed in the following element. Let's see this algorithm operate. We begin by comparing entries in elements 8 and 12 of A, as indicated by the values in begin half 1 and begin half 2 respectively. The entry 4 is smaller of the two, so we copy 4 into the element in temp array indicated by the variable index, and then increment begin half 1 and index. We now compare the entries in elements 9 and 12 of array A as indicated by begin half 1 and begin half 2. The value 8 in element 12 is smaller, so we copy it into temp array, incrementing begin half 2 and index, and then continue with the comparisons.
So just as a reminder, I think you're catching this, but here, this is called merge sort. And right now we're focusing on the merging algorithm. And then we have the sorting algorithm as this divide and conquer.
We continue this process comparing the entries in array A as indicated by begin half 1, begin half 2, copying the smaller into temp array, and then incrementing the respective indices. In this example, our while loop terminates when begin half 1 is incremented past end half 1, thereby indicating all of the entries in the left half have been processed. We now continue with the next part of the algorithm, copying any remaining entries in the other half into temp array, and then copying the sorted entries back into the original array. We need to test which part of the original array, the left or right, still has remaining items to be processed. If begin half 1 is greater than end half 1, we know that the left sequence is empty, so the right sequence has one or more entries remaining to be copied. We use array copy to copy remaining entries from the right half of array A into temp array.
So when you have an even array, both are going to be exactly the same size. If you have an odd element number of arrays, you're going to have one left over, and this is where you're getting a chance to pull in this logic.
After that task completes, we use array copy once again, but this time we copy in order the entries in temp array into the corresponding locations in the original array A. And so when our merge method ends, the client method that called our merge method has a sorted sequence of entries in the elements referenced from the index first to the index last. Now that we have our merge method completed, we can implement our merge sort algorithm. In the client's view of our merge sort method, the client does not need to know we're using recursion to sort the array. For the client, the only important fact is that the array will be sorted using the merge sort. Our public method only needs to have the array to be sorted as a parameter. We'll create the temp array we need for our merge algorithm here, so it's only created once.
So we have this kind of a thing before, because we're using these generics. It's going to say, do you really know what you're talking about? And so that's why we have this, yes, suppress warnings, yes, we know what we're talking about. So you create a temp array of the type T, so whatever they are, if they're strings, integers, whatever they are. And then then once we got that, we set it equal to sorry, yeah, so then we're setting a blank temp array that we're now going to be able to use. We pass A and the temp array, and then we have the start and end that we're going to be using.
Then we call our recursive merge sort algorithm and send it the array our client sent us. The temp array to use for merging, the index of the first entry to sort, and the index of the last entry to sort. Since this is the original call to the method, we send our recursive merge sort the entire array. Our recursive merge sort is implemented as a private method since the recursion is an implementation detail our client does not need to know. The parameters for this method are mapped to the array A, the temp array for merging, the first entry in the current part of the array to sort, and the last entry in the current part of the array to sort. Our base case is an array segment of one entry. If there's only a single entry, we can consider it sorted. In other words, if our array has a single element, we do nothing. So we have an implicit.
So a public merge sort with only two parameters calls a private merge sort with 1, 2, 3, 4, 5, 6 parameters. So we're using polymorphism, if you might remember that term. And so this is where we get into the details of the implementation.
Implicit base case. Our recursion will only occur when first and last are not equal, indicating that we have more than one element to sort. If the array portion has more than one element, we find the middle element and use it to divide the array into a left half and a right half for the recursion. When these recursive calls return, the left and right halves will be sorted.
Okay, so this is an integer. So then we have to be remembering that whatever this is, if we get a 0.5 at the end, it's just going to drop it off. So we're still going to have that midpoint is going to be, so there might be one extra element for the rightmost part of the array that you divided it into.
Our merge algorithm is designed to merge two sorted array segments, so we pass it the original array, temp array, the starting element of the left half, mid, which is the ending element of the left half, and last, which is the last element of the right half. Let's watch this algorithm sort an array of 8 elements. We begin with entries in our array in random order. Our first recursive call passes the left half of the array to the merge sort. The portion passed to merge sort is indicated by first and mid. Each subsequent recursive call divides the portion of the array sent to merge sort in half. So the first action of this current call is to make a recursive call to merge sort to sort the left half of this segment. This call makes another recursive call to sort this segment's left half. And so we process the leftmost elements first. When we get to a single element, we have our implicit base case, and so we do nothing. We now return and execute the second recursive call for this array segment and sort the right half of that array segment. Next, we merge the two halves together and have a sorted segment. Once that merge is completed, we return from that recursive call and continue with the right half of the corresponding array segment. We then merge these two halves together and return with the left half of the array sorted.
So it went by fairly quick, but you can see how you do the divide and conquer. And then you start to bring them together. I went a little bit too fast before I paused it. And then finally you get the lower four elements are now sorted. Okay, so you have the merging, you have the sorting. So we see both of those going on. So first they show the lower half, and then they're going to do the upper half. They're going to have these final 8 digits. The lower half are sorted, the upper half are sorted, and then they'll just do the merging as the one last step to get to the very end.
The recursive call to merge sort for the right half of the array is executed next and sorts the right half of our original array. Now that both the left and right halves of the array have been sorted by the 2 recursive calls, we can merge them together. Once the merge returns, our original array is sorted.
Okay, so we have the code for that. You have those code snippets available to you. And now we're slowly building this out in terms of the performance. The merge sort is actually the best one outside of the radix. And we'll now just go over the quick sort, which is does just as well, except for the worst case scenario. And so there might be some situations where we might not want to go with that if we can use the merge sort by comparison. But let's go ahead and a chance to see this other strategy just to see how it plays out. Okay, what's going on?
This lecture presents the quick sort. The quick sort is another divide and conquer strategy for sorting an array. The quick sort divides an array into 2 pieces, but unlike the merge sort, these pieces are not necessarily halves of the array. Instead, quick sort chooses one entry in the array called the pivot and arranges the array entries so that the pivot is in the position it will occupy in the final sorted array. Entries in positions before the pivot are less than or equal to the pivot, and entries in positions after the pivot are greater than or equal to the pivot. This arrangement is called a partition of the array. If this is our array after partitioning, our pivot would be located in the middle, values smaller than the pivot would be on the left, and values greater than the pivot would be on the right.
So they're not sorted yet, but they have ones that are smaller in terms of an index versus greater in terms of an index as compared to the pivot.
We then recursively sort each partition. 2 common tasks we need to perform are choosing a pivot and then partitioning the array. Here is pseudocode for our algorithm. For now, we'll use a single element.
So we can see we're using recursion. So the method calls itself, and then we do the less than the pivot and the greater than the pivot for the 2 ones that are going to come out of that.
As the base case, similar to the merge sort. Later, we'll change this. As you see in the algorithm, we choose a pivot, partition the array, and then recursively sort the entries smaller than the pivot, and then the entries larger than the pivot. The most complicated parts of this algorithm occur before the recursion. Let's combine the activities of choosing the pivot and partitioning into the method partition. Our partitioning method performs 4 tasks and then returns the index of the partition element, so the recursive call knows how to divide the array. Let's look at how our method can select a pivot. Ideally, the pivot should be the median value in the array so that the subarrays, smaller and larger, each have the same or nearly the same number of entries. One way to find the median value is to sort the array and then get the value in the middle. But sorting the array is our original problem, so the circular logic is doomed. Other ways to find the median are just too slow to use. Since choosing the best pivot takes too much time, we should at least try to avoid a bad pivot. So instead of finding the median of all values in the array, we'll take as our pivot the median of 3 entries in the array: the first entry, the middle entry, and the last entry.
So it's trying to reduce the complexity of finding the quote median and just arbitrarily pick something and just you compare three items.
One way to accomplish this task is to sort only those three entries and use the middle entry of the three as the pivot. Here's a short method, sort first, middle, last, that sorts the entries located at the three elements indicated by the parameters first, mid, and last. It compares the first and middle entries, swapping them if they're out of order. The middle and last entries are compared, and if they're in order, we're done. If those entries are reversed, we need to swap them and then redo the first comparison and swap in case the original last entry was the smallest. Here's an example of our array. First, mid, last method would have received 0, 7, and 15 as first, mid, and last respectively.
So what do you think is going to swap? What do you think with these three ones, which one do you think are they going to swap or not swap? Which one's larger, 25 or 16? Yeah, so 25 will be swapped with 16. They'll be switching places.
Comparing a sub 0 and a sub 7 would result in no swap since 33 is greater than 25. Comparing element 7 and element 15 would result in a swap since 16 is less than 33. Because we are forced to swap mid and last, we must now repeat the comparison for first and mid. In this example, we need to swap the 16 and the 25 since they're out of order. Our pivot will be the mid value 25 in this example. Our partitioning algorithm can now prepare for partitioning, then partition the entries in the array, and finally move the pivot entry into place. Let's look at the entire partition method. As parameters, we send the array and the first and last elements of the segment that our method is to partition. We begin by choosing the pivot. We find the middle element for this segment of the array and call our sort first, middle, last method. When that method completes, the first, middle, and last elements have their values correctly ordered in relationship to each other, but they're not in their final locations. Before the partition entry can be placed correctly, we need to prepare and partition the other array entries into a group with entries whose value are smaller than the pivot entry's value, and a group with entries whose values are larger than the pivot entry's value. We prepare for partitioning by moving the pivot value, or median of 3 value, out of the way so we can partition the other array entries. So we swap the pivot with the next to last element, and we know the last element is larger than the pivot because our sort first, mid, last places the largest of the 3 entries in the last element. And then we save the pivot's new index and value for use later. We now initialize the indices that track our progress in partitioning the entries in the array. The index from left begins after the first element, since we already know that this element is less than the pivot. Index from right begins before the pivot, since that is the first unknown value to partition. We are now ready to partition the array entries. Our index from left is incremented until it references an array entry with a value greater than the pivot. And now decrement index from right until it references an array entry with a value smaller than the pivot. We then swap the two values referenced by the indices. The test in this if statement checks to see if the indices have crossed, which indicates all the entries have been sorted. After swapping the values, we increment index from left and decrement index from right. We then repeat the process and move index from left and then move index from right and swap the entries. Then increment index from left and decrement index from right. At this point, our index from left and index from right have crossed, so we've partitioned the array entries and the outer while loop ends. We've partitioned the array entries into a set smaller than the pivot's value and a set larger than the pivot's value. When we finish the loop, index from left holds the index of the first entry greater than the pivot. To place the pivot in its correct final sorted position, we simply swap the pivot with this entry. Now the pivot is in its final sorted position and the array has been partitioned. And we're ready to recursively process the partition with values smaller than the pivot, and then recursively process the partition with values larger than the pivot. Now that we know how to partition the array entries, let's look at implementing our quicksort algorithm. We pass this recursive method the array and the indices of the first and last elements of the range that are about to be sorted by this call. To begin, we would send the index of 0 for first and the index of the last array element for last. As we'll see shortly, each successive recursive call to quicksort modifies these parameters to refer to either the partition with values smaller than the pivot or the partition with values larger than the pivot. The quicksort works best on large unsorted arrays. If the array is nearly sorted, it becomes difficult to select a good pivot. If a poor pivot is chosen, the performance of the quicksort approaches n squared.
So there's a couple of caveats. It's like, there's no panacea that you're going to create this algorithm that's just going to do everything for everyone. So it's giving some of those caveats. And so you might want to be mindful of that. And as you're doing coding in the future, you'll get a better sense for that, both you and your peers, but you're seeing a couple of things that they mentioned, when it would work well and when it would not work as well.
With repeatedly selecting good pivots that are near the actual median value of the array entries in the segments being sorted, performance of the quicksort algorithm is closer to n log n. An insertion sort is a good choice for small arrays. In fact, using it instead of quicksort on arrays of as many as 10 entries is reasonable. In this if statement, we test the size of the partition we're sorting against some minimum partition size, min size. If the number of elements in the partition is smaller than min size, we perform an insertion sort. For example,
So here, just to let you see, this is a little bit more complicated, but because of some of the liabilities with quicksort actually calls an insertion sort for small elements because it's not going to perform that well otherwise.
if min size is set to 5, and the size of the partition we're asked to sort in this recursive call only has 4 elements, we'll perform an insertion sort instead of partitioning the array again. This can also serve as a base case for our quicksort. If the array partition we are looking to sort has more than min size elements, we perform the steps required in the quicksort. First, we choose a pivot and partition the array entries based on the pivot's value and place the pivot into its final sorted position. After the partitioning completes, we then make a recursive call with elements 0 through 5. In this call, a pivot is chosen, then entries are partitioned and the process repeats. After that returns, we make another recursive call with the entries 7 through 15. A pivot is chosen for that partition and the entries in this section of the array are partitioned about that pivot. With each of these partitions, the recursive process continues. When each of the recursive calls returns, the array entries will have been sorted.
Okay, well, let me just focus on a few takeaways from what we've covered. So we have talked about 6 different sorting approaches. And so we've had a chance to see some video notes on the selection sort, the quick sort, and the merge sort. The selection sort is pretty straightforward in terms of seeing how it works. The merge sort actually performs better, even better than the quick sort. It's about the same except for the worst case scenario. And so the merge sort, maybe it's conceptually not too difficult to sort of get your head around. There's the sorting and there's a merging that takes place, and we walk through that in detail. So we always want to be careful of what happens. You want to go as low as possible, and n is better than n log n, but n log n is still better than n squared or n 1.5. And so we see those kind of things that are out there. Okay, so that gives us a lot of the basis for us to be able to then thinking particular about sorted list. And so that's not an ADT that you're going to be doing coding, but there is some extra credit if you would like to take advantage of that. And so on Thursday, we'll go ahead and talk about that. And also I wanted to leave some time if we haven't done this so far, if you guys want to share some of your code and go over it. We haven't done that for a little while. So why don't we go ahead and leave a little bit of time for us to take advantage of the coding each one of you have been doing. So let me pause and see if there's any comments or questions on what we covered.
One question.
Sure. Okay,
Now, I want to just regarding size, I'm not sure if we have to do it specifically with numbers or if we do it like.
yeah,
Small.
you don't have to use it by, so your question is, remember, we're doing a generic type T, and so we can sort whatever we would want. So if you're sorting numbers, that's easy for us to see. If it's letters, then we have to, A is less than B. So that's where remember we saw that comparable. You have to be thinking about how you're going to compare that. Aardvark is going to be less than Apple because it's AA versus AP. And so that's going to be the thing that you would be looking at. So I would recommend starting simple but you can go ahead and definitely give that a shot. And you can please reach out to me if you have any comments or questions. I'll be glad to help you through some of that. Okay. Any other things that come up? Okay, well, I think that's a good breaking point for today. So